Hello, in this video I will tell you about an algorithm or an approach to solving string problems called polynomial hashing. For example, one of the most obvious problems that can be solved by the polynomial hashing approach is finding a substring in another string. So let's say there is a long string, for example s, and a shorter string, for example t. There is a good metaphor, by the way, that I like to mention. When you name these variables in your code, for example, s and t, it's really hard to remember later in the code which one is the string in which you find the substring and which one is the substring that you want to find. So here with the picture, you see that I definitely want to find an instance of t, a presence of t inside s. But when you don't see the picture, you have two variables and you don't remember the names or which one is which. So I really like this metaphor. Some people use the variables called haystack and needle for the something for which you search and something the place in which you search. And if you name these two strings by these two names, you will have the understanding what you search in which one you search in which one. So the question is how to find, for example, whether the string t is present as a substring in string s. For example, Python does that by the code t in s. It's not very obvious, but specifically for strings in Python, when you ask whether some string is another string, it means substring search. So how do you do it quickly? Or how do you do Control F? It's very common hotkey in very many computer programs. How do you search for some substring in some long text, maybe in a browser or in a web processing program? So how do you search for some text, small, well, presumably small, but maybe large text inside some larger text? And the question is whether there is one or no. So this is true or false. T in S returns you true or false. Or usually most of the algorithms that I can think of also can easily answer the question, what are all the occurrences of T in S? So finding whether there is an occurrence or not is usually not much easier than showing all the positions and like highlighting with yellow color in a browser or something like that. So the stupid approach, the formal, straightforward approach would be to compare t against all the possible positions of occurrence of t inside S. So you can try this position and this position and this position and so on up to the last position. Well, if t is extremely short, or if t is almost as long as S, this actually is a good approach. For a very short, you do almost linear process. For t almost equal to S, you do very small searches, which is okay. But formally, what do? You take a lot of positions inside S of the length equal to the length of t, and you do formally linear procedure to compare. So you take O of t time to search to find out whether this place is an occurrence of t. You do O of t time to check if this position is an occurrence of t, and so on up to the last one. So if S is seriously larger than t, then you do this procedure for many positions, and the number of positions is proportional to the length of S. So except for the well, formally it's, I think, S, length of S minus length of t. But if we believe that t is much shorter than S, then we have a time of work of this procedure equal to the product of their length. So if you are searching for like a megabyte long genome genome part in a gigabyte long genome, then it's like 1 million times 1 billion, so it's like 10 to the 15th, and it's definitely not going to work in a reasonable time. So for long strings, such as in bioinformatics, for example, this is definitely not working at all. So you can object to me that and say that many of these O of t procedures will stop very quickly. And if these are like random strings or natural strings without very strange effects, this is more or less true. If this is, for example, a random string and this is a random string, you will start considering some part of S whether it's equal to t or not, and on the first character, so you're probably doing it left to right. You're probably doing simply comparison of the first character against first character, second character against second character, and so on from left to right. So you do it in formally linear procedure, but in many real life scenarios, you will say that with high probability, the first letter will already be unequal to the first letter here, and he will stop this procedure not doing t operations, by doing just 1, 2, maybe 3 operations and stopping because the letters are different. So if you take some actual book from my bookshelf and try to search for the text of this book in some other random books, usually you will stop very quickly by seeing different letters. So in practice, this straightforward algorithm can work indeed much faster, but of course it's no, not of course, but it is indeed possible to find the example in which such working time is reached. So the simple example would be to search inside the string of all the letters A. So there is a like 1 billion long 1 billion character string of letters of A, and this is S or haystack, and the needle or T that we are searching for is a lot of letters A and then letter B. For example, 1 million letters A and then one letter B. So this is a very important and very simple to invent example. So for each position in S, you will do a lot of work to check whether this position is equal to string T. You will do, if you are doing left to right search, you are taking almost all the, well, actually all but one letters and continuing the process because you see that the letters are equal. And only in the last letter you say, oh, this letter doesn't equal this letter, so this is not an instance of T. And you do maximum possible number of operations, and you would do it for each position, so you reach the maximum possible working time. So there are examples in which the working time is the product of this length. So if they are both like millions or billions, you are doomed to a very long procedure. However, I know that many computer programming languages and computer systems unfortunately do exactly this straightforward search. So it's rather strange, but in some programming languages, if you try to search for this string inside this longer string and they're all like million or billion length, you will not receive the result in reasonable time. That is quite strange, but that's what happened. There are there are strictly working deterministic algorithms that solve this task in time linear of both lengths. So this is possible. For example, I must mention Knuth-Morris-Pratt algorithm that is definitely searchable in textbooks or Wikipedia. So there is an algorithm that definitely works, and it's really good. It's really good for implementation and useful. But in this video, I would rather teach you another approach that has a little problem. I will tell you about the problem of the approach, but it is much more useful, much more fruitful, because many more problems are solved by the polynomial hashing approach rather than a few problems that are wonderfully solved by Knuth-Morris-Pratt algorithm. So learn that as an extra material, but our material is an approach that helps you solve this problem as an example, and many more problems as a free consequence. So once you implement the thing that I'm going to teach you, after that you freely can solve many problems in a very short time. So the procedure will be rather quick. What is the approach? So we see the word hashing, and we know that hash functions are some functions that are applied to strings and that map them to some integer numbers. So in the lecture about hash tables, I didn't tell you about what are specific algorithms in Python or in other programming languages and or other system. So now comes the time when you learn how in many programming languages a hash of a string is calculated. We are not going to take these integers of arbitrary size. So in Python, it's easy to support, well, Python freely supports logarithmetics, so you can take over here huge numbers. But if your hash function is allowed to map your objects to huge numbers, it's not really useful, because the hash function should be in some reasonable range. Otherwise, for example, you just can consider your string as a very long number and say, okay, this is the integer that is a hash function of my string. So it will be not, it's not something mathematically smart, it's just formal procedure. And you say, okay, here is a wonderful mapping from strings to integers. But in this case, these integers have a huge length. The length of the resulting integer is equal to the length of the original string. So nothing cool happens over here. And it's just rather mathematically stupid to allow yourself to have integers of huge length encoding these objects. So these integers should be of a reasonable length. And in our case, it will be very simple. Our integers will always be inside the interval from 0 inclusive to m exclusive. And even more important, we will just have everything in our lecture taken modulo m. So we will do all the integer arithmetics, taking every step in every operation by modulo m. We will be working only with positive integers. So, well, in Python you don't have this problem. In Java and C++ you can have a negative integer giving negative remainders, which is a strange thing, but anyways. So we are working with positive integers. We are taking each time everything modulo m, just working with remainders modulo m. And so all of our numbers will be between 0 and m minus 1. So taking everything modulo m is not a hard thing to do. If you have never thought about this, then you can think about, for example, working with large numbers, but taking only the last digit. So you can take the year and add some random number, the answer to all the questions. And then instead of, so the formal answer would be like 263. But when working with large numbers, you can do the modular arithmetics by modulo 10 and say that the first number was simply a 1, the second number was simply a 2, and the third number was simply a 3. So in modular arithmetics, all the numbers that end with 1 are mapped to a 1, all the numbers that end with 2 are mapped to a 2, and the sum of 1 and 2 is 3. And more interestingly, the sum of 3 and 9 is equal to 2, because, well, actually 3 and 9 add up to a 12, but in our world, in the world of all the integers taken modulo 10, the answer is not 12. Well, the answer 12 is also correct, but the answer 2 is the best formulated answer, because we only work with numbers 0 to 9. So in this world, modulo 10, 3 plus 9 is simply a 2, and for example 3 times 9 is what? It's 27, so it's simply a 7 in the world modulo 10. So instead of numbers, we work with their last digits. It's most simple example for usual people who start learning modular arithmetics, I think. And so algebraically, you don't need m to be equal to 10 or to some small number. You can do the same modulo some other large number n. So we will do a lot of operations modulo m. Now, what do we need to learn about hashes? A hash is a hash function. A hash function h is definitely a deterministic function. That is, it's a procedure to calculate some integer based on some string without using random numbers, files, keyboard input, network, internet, anything. So this should be a procedure that all on some specific string s definitely returns some deterministic exact integer. And if we calculate the hash function of the same string several times, of course, we want to receive the same result. And so equal string. And if you have the string received in some other way, like for first time you have a string, and in some other part of your program, you have two halves of the string concatenated, and you receive the string that equals to this string, original string. But in terms of, for example, Python memory, these are two different objects. It's a normal situation. You can have in your Python code two objects showing two strings being equal, but the links to them are different. So there is one instance of this string and another instance of the same string, but these are two different objects. So definitely we want the hash function applied to these two different objects to return the same integer. So this is purely a mathematical function. On equal arguments, it returns equal results, definitely. But what if t is a different string? So for s unequal to t, we want the hashes, and not only in this topic, the polynomial hashing, in any hashing algorithm, in any applying of hashing in computer science, you want this to be, let's say, different with high probability. That's the best thing I can say here. So we take we use the mathematical, the part of math called probability theory or statistics, and we say that we cannot be promising that these two values are definitely different. Well, in fact, we can do it if we allow huge integers. So if you allow strings of length 1000 to be mapped into integers of length 1000, then it's indeed probable to have such system where different strings definitely, for sure, have different hash functions. Once again, just consider each string as an integer, and that's it. But if you want to have the values of your hash function limited by some reasonable threshold, then just by the number of the sets, by the cardinality of the sets argument. So think about the cardinality of the sets. There are very many strings, long strings of length 1000, if you can count, and it's a huge number. And there are just a few numbers from 0 to m-1. So definitely by a pigeonhole principle, or just by simple reasoning, some strings should definitely fall into the same integer when this procedure is applied, when the hash function is applied. So it's very normal that different strings have indeed equal values, equal hash function values, and such situation, when they're equal, is called a collision. A hash collision, which can be a problem. For example, I can tell you about real life. Like in real life, when you download a huge file, it's a wonderful tradition and it's a wonderful practice to also, the person who publishes the huge file also publishes the hash function of this huge file, a reasonable size integer showing some characteristics of the huge file. So when you download this huge file, if some of the bits are corrupted just because the wires are imperfect or something, or the TCP/IP packages just didn't come in correctly. So formally, probably the file is corrupted a little bit. And then you want to calculate the hash function of a corrupted file, and you definitely want to see another result and say, okay, I didn't download the file correctly, I see a wrong hash function, let me re-download or do something about that. So this is a normal situation. If you see that the downloaded file has the wrong hash, do something about it. But unfortunately, with a small probability, formally there can be a collision. So you will receive a corrupted file with changed zeros and ones, but the hash function is exactly the same. So you see look at the hash function, you say, okay, the hash function looks good, probably I received the correct file. And you are wrong because you have seen a collision. Well, but usually in good hash functions, this will not happen arbitrarily because the probability is really low. But please remember, please understand that this can happen by the actions of some bad person. If some bad person in the middle, like a bad internet provider or bad browser author or someone gave you a very specific bad file, it can be possible that by their bad will, they decided to give you the, for example, executable file that is also an executable, but does, for example, the same function as your original executable file, and also brings in some malware, some computer virus. And if they're smart enough, they can make this executable file have the same hash function as the original executable file. So if the hash function is not secure, then the bad people can give you an executable file with the same hash functions, so they can make a collision by their own hands, I mean, not manually, but automatically. If a hash function was bad, they can send you a wrong file with the same hash function. So you should be aware of that. And the humanity should make hash functions for which finding such file is an awfully hard task. So we'll not be talking about secure hashes in this lecture, because I'm aware that the hash that we are talking about is not secure. It's definitely mathematically possible to find a collision, specific collision for this hash. So this hash is not for security reasons and for checking the file checksums or something, but for other tasks. We will be solving string algorithm. Look, the part of computer science that is responsible for this is called string algorithms, and we will be solving problems from string algorithms using the polynomial hashing. So we are going to invent some hash of a string that maps a string into an integer modulo m, like from 0 to m, not exclusive. And let's try a polynomial. So finally, the definition. Let's say that our string s is, well, let me be a programmer here, so I will start the indexing from 0. So we will have first letter, second letter, and so on, the last letter. So I just denoted the letters 0 to n minus 1. As usual in computer science, n is the size of the collection. We have exactly one collection, our string that we are working with. So as usual, n is the size. And we say that we use these letters as coefficients of the polynomial. How can you use a letter as a coefficient of a polynomial? Well, in our topic, I will be just simply understanding characters as integers. So instead of saying that I have letter A or like P in polynomial, I would rather say that this is a letter that have ASCII code or Unicode number equal to like what's it, 60 something, I don't remember by heart, the ASCII code of letter P or the Unicode code of letter P. It can be easily found in the internet. So instead of letter P, I will say 68. And so each letter now becomes an integer so that I can use these letters or digits or punctuation marks as integers. So I'm just in Python code, instead of a letter SI, SI written like this, I rather use word of SI. So instead of any any character, I rather use its order in the Unicode table. So my string is a list of integers. And this list of integers will be used exactly as coefficients of a polynomial. So let's do it. Let's say that S0 is the leftmost coefficient. So in European tradition, we write the largest degree terms to the left. So I multiply it by x to the power of n minus 1. The next letter is multiplied by x powered by n minus 2, and so on. The next to last n minus 2 letter number n minus 2 is therefore multiplied by x in which power? So 0 plus n minus 1 is n minus 1. 1 plus n minus 2 is n minus 1. So the index of the letter and the power of x always add up to n minus 1. So n minus 2 plus 1 is what we need. So for index n minus 2, I have a power 1. And for the last index, I simply have power 0, which is a 1. So I could have omitted the x to the 0th product, the factor over here, because it's simply 1. But it is more consistent to write like this. And, well, should I use the red marker? Probably. We are doing everything modulo m. So probably, well, my whiteboard is not wide enough, but I should really, or you in the note, should really take this in parentheses and say, as usual, modulo m. Well, okay, let me do it for the first time. So this, okay, let me do it in the red marker, so you can do it. So it's something obvious that we do throughout the lecture. This is, of course, taken modulo m. All right, what could, so when we say that our strings are hashed by this system, the polynomial hashing, we should just select parameters of the system m and x. So when we say that we use polynomial hashing, we say like m is 7, x is 3, which is a very stupid thing because all the strings will have hashes 0 through 6. But well, some integers, and once you have selected m and x, and also once you have selected the order, so some authors do it the other way. They say that the left letter is multiplied by 1, this letter is multiplied by x, and so on. So x, the powers of x grow from left to right. It's possible both ways. Let's just stick with the one of the two alternatives, that this is multiplied by 1 and this is multiplied by some huge number. The x to the maximum, the power n minus 1. Once you have selected two specific parameters m and x, then you have a specific system of polynomial hashing. You have for each string calculatable in a linear time so far value, the hash of its function. Well, even to calculate this in linear time, it's not a very easy task for a novice person, because you need a lot of powers of x. So to do it in linear time and not quadratic time, what you should do is calculate it from right to left, I think, and bring with yourself the value of x to the corresponding power. So you have this variable that starts as a 1, and once you go right to left, you have this variable equal later to x, then to x squared, and so on. So you when calculating these terms, you bring with yourself this factor, and it's easy because each time you simply multiply it by x modulo m. So you bring it with yourself, and each time you take this factor, multiply it by the corresponding letter, and add it to the answer taken modulo m. This way, in linear time, you can calculate a polynomial hash. But this is only the start of some of our miracles. So linearly calculating hash function is quite simple, too simple. Because please think about the procedure of calculating the hash function of some prefix of s. So consider the string t, let's use the letter t, equal s0 and so on, s to the power m minus 1. So I took m first letters of my string t. Once again, the main collection has size n, and another collection always has the size m. It's the letters used in our science. So let's consider hash function of t. Well, formally, let's see. S0, the first letter, is multiplied now. So what is the power of x to which is multiplied by the leftmost letter? It's the length of the string minus 1. So here we multiply by x minus 1. Here the next string is multiplied by x minus 2, and so on. The m minus second character is multiplied by x to the power of 1, and the m minus first letter is multiplied by x to the power of 0. What is the similarities between these two two polynomials? These are two polynomials of variable x. So what are their similarities? Well, look at it. This term is quite similar to this term, but their difference is, so this is x larger than these terms by x to the power n minus m. And this term is also larger than this term, and if you divide this one by this one, the ratio is once again x to the power of n minus m. And so on. This term also is present somewhere over here. And once again, here s with index m minus 1 is multiplied by x to the power n minus m. So this polynomial is almost present somewhere around here. So the polynomial for a larger s has inside it in some way the polynomial for a shorter prefix. Now, when we see these terms more or less, well, in some way present over here, let's multiply this polynomial by the corresponding coefficient and subtract from this part. So here comes the magic. It can be told from the other way, but let's do it this way. So a prefix can be multiplied by x to the power n minus m and can be seen over here. So, okay, let's subtract h to the power of s minus, or the h of string s minus this polynomial multiplied in such a way that we receive exactly these terms. So we multiply it by x to the power n minus m. And what do we have left? We removed all the terms over here that correspond to these letters, and we are only left with the terms that correspond to the letters that weren't present in t. So all these letters, let me do it in green, all these letters are subtracted. The terms corresponding to these letters are exactly perfectly subtracted, and we are only left with the terms corresponding to all the other letters. So the first m letters, they had the terms over here, and we removed these terms because we took the corresponding terms multiplied by exactly the good power of x. So all the terms are removed, and for the last letters we received such a polynomial. So we receive a polynomial where the last letter is multiplied by x to the power of 0, the previous to last letter is multiplied by x to the power of 1, and so on. So what do we receive? We receive this very type of formula for the last n minus m letters. So this is exactly this was the definition of our hash function, and what we receive left over is exactly this definition applied to the last n minus m characters. So this is a hash function of the string s from which we take indexes from m to n minus 1. And this is in fact the most important, I think, formula of our lecture, because this is some suffix of our text s, and in fact this suffix can be expressed, well, the hash function of the suffix can be expressed as the some not very hard to implement formula containing the hash function of the so this suffix is expressed in terms of the entire string and this prefix. So if you want, here is the main part. If you want to calculate the hash value of some string, the red string, you need to know the hash function of the entire string and of this prefix. So hash function of each, well, suffix of s is wonderfully represented by a hash function of the entire s and the prefix of s. And what about not only suffix of s, but any substring of s? So if you take s, and if you think about any red substring of s, the hash function of the red substring can be expressed in terms of this prefix and this prefix, because if we write this down for the longer prefix, then you take the longer prefix and the shorter prefix, and you receive the difference between them, the red substring. So using this formula, the hash function of any substring s can be expressed in terms of hash functions of only prefixes of s. So what you need to do is, okay, let me remove the red part. You need to take all the prefixes of s and calculate the hash functions of all these prefixes of s. And once you do this, all the hash functions are fully calculatable. By all the hash functions, I mean all the substring hash functions. And using this one, yes, that's already important. And also you should see that using this formula, it's not hard to relate a longer prefix to a shorter prefix. So using this formula, we can also express a longer prefix. It should be not hard to express it from the prefix that is smaller by one letter. So let's call these prefix hash functions an array P, So the array P by definition Pi is just hash function of the first I letters of S. So we will calculate the hash function, this very hash function, for prefix of length 0, of length 1, of length 2, and so on. This will be an array of linear length, but it's okay because the string itself has the linear length. Like if the string is of length million, it's okay to store 1 million integers together with the string. Why not? So maybe in some applications not okay, but generally 1 million characters, why not 1 million integers? And so let's find the formula for this Pi. Well, the formula will be rather recursive, yes? So we will express the prefix function of some prefix in terms of a previous prefix, of prefix by one character shorter. So in recursive functions, we don't want to have always the recursion. So there should be some special case, and indeed P0 will be a special case. Formally, what is the hash function of the prefix of our string f of length 0? So this is an empty string, and we over here have an empty sum. The empty sum is the sum of the empty set is a 0, so we have an honest 0 over here, and that's it. P of 0 is equal to 0. I would rather store it in the integer array, but if you really want to save the space, I don't know why, but it can be, you can just omit this element and say that it's simply 0, but I definitely want to store this. And now let's find the ith element. So what is the hash function of the any prefix of length I? Well, if we put this term to the right part, we see that this is the hash function of a smaller prefix. Oh, let's actually write it down, but I can write this down right away. What I do is just I put the subtracted term to the right side. So the hash function of a longer prefix is the hash function of the shorter by one prefix, I minus 1, p with index I minus 1, multiplied by x to the power of the difference of the lengths. So this is like the important formula from which we can retrieve a lot of other things. Here we have x to the power of difference of their length. So the difference of their length is 1, so this is multiplied by x. And I have to add the hash function of a string that is the difference of these two prefixes. The difference of these two prefixes is simply one letter string, the letter over here, the letter that is their difference. And the hash function of one letter is this letter multiplied by 1. So it's simply this very letter. So we add over here this very letter. Let me not make a mistake with this index. So we need the letter that is present in the prefix of length I and is not present in the prefix of length I minus 1. So the last letter of this prefix has index I minus 1, and it's important. So in programmer enumeration from 0, I use I minus 1. Indeed, it's very good because to calculate, let's check p first, p of 1. P of 1 should be prefix of the hash function of the prefix of length 1. Well, we take a 0 multiplied by x plus s0 plus the first character. So indeed, the prefix function of the prefix of length 1 will be simply the integer value of this letter, and then it will grow and grow and grow. So we more or less calculate this polynomial by taking more and more terms into account. So from left to right, we calculate the polynomial, and in the end, we receive also quite freely, like in this array. Also, the last element of p is just by definition the hash function of the entire string. So this is as simple. This is exactly so simple. Well, once again, I didn't write down modulo m. Maybe I should. So of course, each time you do everything modulo m. But then it's that simple. This array is calculated as 0 in the beginning, and such a short formula, such a simple formula for any cell of p. So we calculate with a simple formula all the hash functions of prefixes of s. And now, by this formula, we have such a cool thing as, well, maybe let's rewrite it where I don't need t anymore. I don't need the t. So now any substring of m can be expressed, the hash function of any substring can be expressed in terms of, let me restore the red part. So any hash function of any substring is expressed in terms of such prefix and such prefix. Let's find this for, let's just rewrite this once again using the array p. So, or just I'm rewriting the same from right to left. The hash function of any part, maybe not n, yeah, maybe not n, I'm sorry, let's use k as a. So if you take the substring with indexes from m to k, as usual in programming, last index not inclusive. So if you're working with a Python range or Python substring or Java substring, from m to k, you take from your string s a substring with indexes from m to k not inclusive. Then, just by this formula, you need to take the hash function of a prefix containing this substring. So you need to take the hash function of the prefix which has the last character k minus index k minus 1. So this is a prefix of length k, and this is its hash function is already stored in pk. And you need to subtract the hash function of the prefix of this size. So this is the prefix that doesn't contain the mth letter. So it's the prefix that has the last. So I can write down. So this is index m over here, and this is index k. So we are expressing the substring from m to k in programmer enumeration. And this is the prefix of length k, and this is the prefix of length m. It's really a bonus of programmer's enumeration. So a substring of from m to k in programmer's enumeration is indeed a difference between the prefix of length k minus the prefix of length m. So there are no plus minus 1 error over here. So this substring is the difference between the prefix of length k and the prefix of length m, and the formula is that simple. So we take the prefix of length m and we multiply it by what? By x to the power k minus m. If now I want this formula to work extra quick. I want this formula to give me the result momentarily, instantaneously. So if I calculate this with a long procedure, I will spend time. So let me pre-calculate in the beginning of the program all the reasonable powers of x. Since x is a very specific parameter, I can just spend some time in the beginning of a program to receive many powers of x pre-calculated. So I calculated by x power number k minus m. And that's it. That's the main formula. So I was telling you, like, quite complicated algebra, but you don't even need to implement this long algebraic thing, the long polynomial calculation as in straightforward way. You need to implement this simple formula to calculate the array pp, array p, well, you need to pre-calculate powers of x, which is just a very simple for loop. And once you have x powers pre-calculated and p array calculated for the specific string, you can take any substring of your string, and the hash of this substring is calculated with one multiplication and one subtraction. And of course, taking the entire thing modulo m. Once again, definitely in each operation. So to take the hash function of any specific substring, you need 3 operations. And finally, we receive the wonderful result that hash of any substring takes O of 1 time. We have a system where a hash of any substring is calculated in linear time. Well, you have to spend some time for pre-calculating the p array, but if you have done so, like you work with a genome of length 1 billion. Once in the beginning of the program, you spend time calculating 1 billion plus 1 different powers, because you need these indexes from 0, these degrees from 0 to 1 billion. So it's 0 to billion possible degrees. It's 1 billion plus 1 different powers. So you spend billion operations to calculate the x power array. Oh, how do you do it? Of course, I want you to calculate each x power value simply in terms of the previous value. It's a very simple math. Of course, when you need to calculate x to the power of 10, you just use previously calculated x to the power of 9 and multiply it by x to receive the next x power. So x power is a very simple for loop that takes 1 billion plus 1 operations, and then you do 1 billion plus 1. It's very symmetrical. So you do 1 billion plus 1 operations of this type over here, and you receive, you spend 1 billion, no, 2 billion plus 2 operations, and you receive the system which allows you to calculate the hash function of any part of the genome with a very simple, very short formula. So now we have strings, substrings. For any substring, we can calculate its hash instantaneously. What can we do now? Well, let's first of all solve the substring problem. And to do this, I will tell you that we can save the specific m and x values and do such thing for one string s and for another string t. This is also a fully possible behavior. So we pre-calculate the prefix hashes for s in one array, in one list. We pre-calculate the prefix length of t in some other array. And for what can we do now, for example? Let me draw t a little bit shorter than s. So how do you find search for t in s? Well, you search over all possible positions over here. And now you want to check if t is exactly present in this position. In the original straightforward procedure, we spent linear procedure, linear search over the indexes to check if this character is equal and this and this and this and so on. But in this algorithm, you take the hash value of this substring by this simple formula. Actually, you just need to know the hash of t in this case. You calculated also the hash of t, and you compare if they are equal. If the hash function of this substring is different from this hash function, then definitely this string is not present over here. And if they are equal, well, either you ran into a very unbelievable collision, which can be estimated how probable it is, But for real life strings, it's absolutely improbable. So you can well, very simply speaking, simplifying the math part, the probability theory here, this is some number from 0 to m exclusive, and this hash is also some number from 0 to m exclusive. So very stupidly saying, the probability of collision is 1 over m, because some random number from 0 to m and some other random number from 0 to m, they randomly collide with the probability of 1 minus m, because once you have fixed this number, this is kind of a random number of m possibilities, so the probability to match this fixed value is 1 over m. So if m is like much larger than your reasonable number of operations, then this can be negligibly small for real life purposes. Or for harder mathematical tasks, you can consider that this is a good approximation and calculate formally what is the overall possibility of you having an error here or here or here. But if you believe that this is almost zero, then you simply calculate the hash function of this substring, this substring, this substring, and so on. Each hash function is calculated very quickly, and you take like O, not like what exactly, you take O of 1 time to check whether the hash function of t is equal to the hash function of this substring. And when you see two equal hash functions, you say, okay, I can highlight this string in yellow because over here I found this string. So this algorithm takes linear time of s to calculate the p array over here, linear time of t to calculate the hash of t, and so the total time is the sum of the size of s and size of t. So if this is billion and this is million long strings, then it's like 1 billion plus 1 million operations, and not 1 billion times 1 million operations, which is way cooler. So it can be a genome. This can be a part of the genome, and you can compare them easily. Or you can take one long string s over here, and compare its parts whether they are equal or not. So if you want to search for repeats in your text, like for example, you can search for your code base to find repetitive code, the copy paste, and remove it by extracting it to a general function. You take your huge GitHub repository and you find for similar parts of code. Or you take, for example, all the work of many students in a university and you search for large repeating parts. So if one student has copied the work of another one, or if one author in not in education but in science has made a plagiarism from another author. So in straightforward situations, you can use linear search to compare this against this each time. But in our new algorithm, now in our new approach, you can simply take any substrings, and in instant time, you can calculate this hash and this hash, and return the answer whether these two parts are equal. Well, can you believe it? This can be a part of length like 1 megabyte, this can be 1 megabyte, but you don't spend 1 million operations to check if these 2 megabytes are equal. You spend 3 operations, like a kind of 3 operations, to say if these two parts are equal. Formally, you don't tell the correct answer. Once again, if the hashes become different, if the hashes outcome to be different, then you say, okay, sorry, these two, no, not sorry, these two substrings are definitely different. But if they are equal, if this gives you hash function h1 and this is also h1, then it's either these two substrings are indeed equal, or they're different, but you found a very improbable collision. Well, if you find not a lot of plagiarism inside your university, then you can just spend linear time after that searching whether this string is equal to this string in the usual equals operation of your programming language. So once you found some substrings of equal hash function, you may either believe that collisions are improbable and say, okay, these two are doing plagiarism, or you can better by the innocence presumption, you rather spend the linear time to check if these two substrings are indeed equal. Okay. Also, this can be like mathematicians also like this problem of finding palindromes. So if you want to check, a palindrome is a word that can be, or part of the word or part of the genome. In bioinformatics, there are some important palindromes in some way. So you want to check if some string is equal to itself reversed. It's also a hard task to find large palindromes in a text, but let's now understand that we can very easily check if some substring is a palindrome. So as I told you, once you have fixed the m and x values, you can do this p array calculation for many strings. So you can take s and calculate the p functions for all these prefixes. And you can take s reversed and calculate the p functions for all the prefixes of s reversed. Once you have done this, how do you check if some substring is a palindrome? You take in a very short fashion the hash function of this string, because you just take this prefix, and from them you simply calculate the hash value of your string. And also you easily find the index of reverse of your string in the reverse of string s. So if string s is over here and h is over here, it's a very simple task to find the indexes of your string revert somewhere over here. In this example, my original string was rather in the left, so the reverse is over here rather in the right. And you take this prefix and this prefix. So by our usual procedure for any string, because you have pre-calculated this prefix hash and this prefix hash, you also calculate this hash, like h2. And if they are different, you definitely know that the original string was not a palindrome, because a palindrome would have some hash of it over here, and here it will be reversed into the same string, and the same string would definitely return the same hash value. So if you see these two guys different, then it's definitely not a palindrome. And if you see these two guys being equal, then, well, either you are into a very interesting collision, which is very improbable, or you have found a palindrome. So once again, isn't it beautiful? You take a large part, like you take 1 billion part of a 2 billion string, and you answer the question whether this 1 billion part is a palindrome in O of 1. You take like 3 operations over here, three operations over here, compare to integers, and say, okay, this 1 billion long substring is definitely not a palindrome. This is very beautiful, I think. So this is the idea of polynomial hashing. You can also, if we are speaking about searching substring t inside substring s, this is also called in textbooks Rabin-Karp algorithm. So Rabin and Karp are the inventors of the idea that you can take a hash of t and try to find the substrings of the similar length. Well, rather take all the substrings of similar length, calculate their hash functions, and those who have equal hash functions are the instances of t in S. This is called Rabin-Karp algorithm for substring search. But for overall idea, this is called polynomial hashing. And this can be, well, let me just recall what we have learned. For any string of length, for example, n, you pre-calculate a lot of powers of x, being just x to the power of 0 is 1, and each next power of x is the previous power of x multiplied by x. So this is a linear procedure to pre-calculate all the powers of x. This can be done for many strings. If you are working with many strings, you can have a common array x power for all the strings. It's common among them. And then for each string with which you are working, you calculate this wonderful array of p, well, the prefix hash functions of prefixes of this string. So this is an array of length n plus 1. First, the 0th element is 0. Each next element is calculated superbly simple. I omitted on the whiteboard the fact that here you work with ord of this letter, so this can be a character type in your programming language. You rather take the ASCII number or Unicode number of this character over here. And I omitted, or rather have made it red. So you do this definitely modulo m, and all of these definitely modulo m. So this is, the formula is like one line over here and one line over here, and both lines are short. So you calculate this p array for each x, for each string that you have. And now, using this formula, you can calculate any hash for any substring of any of your strings. So you can take different substrings of one string and compare them in O of 1 momentarily, instantaneously. And you can take two different strings of substrings of different strings and compare them if they are equal in an instant time. Also, a good question is, what are m and x? Well, if you take small m, the problem is that collisions will happen quite often. If you take m like 10, then you classify all the strings in the world into types 0 through 9. And then it's very easy that some of the, like if you have 11 people in a group, then by pigeonhole principle, some two of them will have the different names and equal hash, which is just collision out of the box. It's very bad. So m should be larger, much larger than the number of elements in your system. So it's like something seriously larger than the sizes of your collections. And what can be the other problem? X and m shouldn't have common divisors. The easiest example that I like to show, and I will actually talk it through, is the best, the worst case is the best example, and the worst case if m is divisible by x. Imagine that m is divisible by x. For example, you can take m equal to the large power of 2, because it looks quite easy to make all the calculations modulo some power of 2. And you decided to make x not only even, but just simply also a power of 2. Then think about these x powers. At some point, the x to the large power becomes simply divisible by m. So this number, if you take quite a character from a left part of the long string, then this is 2 to the large power, and it's simply divisible by m. So in this world taken by modulo m, this will be a 0. And so your strings, the hash function of your string, will only depend on the rightmost letters. So like all the strings that end with 1000 exclamation marks, it's not really a good way to express your emotions probably, but if you have one fiction book ending with 100 exclamation marks and another fiction book ending with 100 exclamation marks, you will simply have them as if they are equal. Well, according to the hash functions, they will be considered equal because left characters do not are multiplied by 0 if you take in modulo m, and so they do not actually impact the hash function at all. So it really looks very stupid. So that's the exaggerated example, but generally I would rather recommend that advice that m and x are co-prime to each other. They don't have any common divisors. And probably the easiest way to do it is to make m prime and x just smaller than m. So you take like some small number x, you take a larger prime number m, and it's good. Also, well, the last idea is x shouldn't be very small. X should be larger than the size of your alphabet. X should be larger than the size of your alphabet, because if you take x, for example, 2, that's also a very simple example. So consider you took m, a huge odd, obviously, prime number. You take a larger prime number, obviously it's odd. And you decided to take x equal 2. Then consider two strings. Well, consider some string, and this letter is multiplied by a 1, and this letter is multiplied by a 2. So if I add a 2, if I increase this letter by 2, and I decrease this letter by 1, then this term is increased by 2 times 1, and this term is decreased by 1 times 2. So by simply working with your first name, I change your last letter a little bit, I change your previous to last letter a little bit, and I receive another name, another normal English word that has the same hash function. So if a small x is used, then it's easy to make collisions. It's easy to make reasonable English words with similar hash functions. X equal to 1 would be even worse. For x equal 1, all the letters are taken with the same coefficient. So for example, any anagrams, any words with the same letters will have the same hash function, right? Because it's just the sum of all the letters. So I'm not sure about English word names, but in Russian I know Nina and Inna are the actual Russian famous female names that will have absolutely the same hash function, because all the letters are multiplied by 1. So small x is really a bad strategy. So x should be a mediocre size number, and m should be a very large number, definitely not divisible by x. So why not take m equal to prime number? If you are very used to limited integer types, you can think that m can be large power of 2, because you can say that in languages other than Python, it's very natural to make operations modulo 2 to the power of 64, like in long type of C++ or Java. But there are interesting mathematical counterexamples where m equal to power of 2 work in a bad manner. So they have very natural collisions. Interestingly enough, it's called Akhmedov effect. I think it's correct to call it that name. So for m equal to power of 2, there are very natural collisions. So please do not use the long type calculations over here, but rather use m equal to prime number, some large prime number. Well, some languages actually allow you to create. There probably in your programming language there is a function to generate a prime number of such and such size. So generating large prime numbers is not hard, or you can just hard code a very specific large prime number m into your program and a very specific not very small number x to your program and receive this system. So now you have all the strings converted to integers by this system, and also any substring of your strings also is instantaneously converted to the same to the integer by the same rule, but although this rule looks linear, it looks like the calculation of hash function is linear, but by our smart algebra, we can calculate the hash function of any substring, not in linear time, but in constant time, which is a great invention. So I hope this can help you in real life processing of large texts. I know for sure that this is indeed used for large files, for genome processing, for bioinformatics and large text. Well, in many areas of computer science and applications of computer science. So it's good to know these principles and these approaches. Thank you for your attention. Goodbye.